All right, guys, this is a quick video tutorial on the ideal gas law. Okay? Now, we have talked already about the very basic gas laws, right? So we've talked about Boyle's law, which is P1V1 equals P2V2, or in other words, pressure and volume are inversely related. We talked about Charles' law, which is that volume and temperature are directly related. We talked about Avogadro's law, that moles of a gas and volume are directly related. And I don't know if we got to it or not in class. I can't remember. Gay-Lussac's law, which is pressure to temperature is directly related. So in other words, everything is a direct relationship except pressure and volume. Okay? Now, if you remember, these relationships only hold true, right, when the other variables are held constant. So for example, with Boyle's law, right, pressure and volume can change, but this relationship only holds true when moles and temperature are constant, right? And so on and so on. So let me give you an example of how this can get messy. So let's take Boyle's law. We have a container. Okay, let's say we have a container of a certain amount of gas particles, right, at a fixed pressure. What if I cut that in half, right? So I have the same number of particles, right, but I've cut the volume in half. What's going to happen, right? If I cut volume in half, pressure should double, right? That's that kind of inverse relationship. Volume gets cut in half, pressure doubles. Okay, well, if pressure doubles, right, this law says that temperature doubles, right? So we have volume halving, pressure doubling, temperature doubling. Okay, well now look at this one. If temperature doubles, shouldn't volume double? But we all said the start of this whole thing was that volume halved, right? And so that's what I mean by this. This gets messy really quickly. And these relationships only hold true when the other variables are constant, okay? So these only work when these two particular variables are changing. So what do we do when more variables are changing? And that's where you have the ideal gas law. Okay? This is the ideal gas law. This incorporates all four variables that we want to talk about. We have pressure, right? We have volume. We have number of particles or moles. We have temperature. And then we have the R value, which is the constant. Okay? So R is a constant. I'm going to give you that value, right? So P, obviously pressure, V, volume, N, moles, T, temperature, and then R is a constant. It's actually called the gas constant. And so R equals 0.0821. This is a big unit because there's actually 4 different units within this formula. We need a pressure unit, we need a volume unit, we need moles, and we need a temperature unit. So we actually need 4 units here. So the unit here is liters, atmospheres over mole Kelvin. So it's a big unit, right? This is the value for R. And like I said, that's a constant. Now, if your units are not liters for volume, atmospheres for pressure, moles, and Kelvin for temperature, then you have to convert into those units to get the R value to cancel out. So there is some work you might need to do to get this to work out, but this is the general rule, okay? So let's try practice. Okay, so this is from chapter 6. This is number 37 from the back. What volume is occupied by 0.188 moles of helium gas at a pressure of 0.97 atmospheres and a temperature of 305 Kelvin? And the second part of that is, would the volume be different if the gas was argon? So let's tackle the second part of this first here. Right? Would the volume be different if the gas was argon under these same conditions? This goes back to the kinetic molecular theory. The answer is no. The volume would not be different if it was argon, because the identity of the gas doesn't matter. Remember that the volume of the actual particle is insignificant in reference to the whole container. So whether it's argon or whether it's helium or whether it's whatever, okay, the volume actually is going to be the same as long as the conditions are the same. Temperature, pressure, and so on. Okay? So let's tackle the first part. So we have PV equals nRT. We need to use this formula because if you just look what you have, we have one thing in moles, we have one thing in ATMs or pressure, we have one thing in temperature, and we're asking for volume. So we have one of each unit. The only formula that helps us with that is the ideal gas law. Okay? So they're asking for volume, so I'm going to rearrange the equation. Okay? And I'm going to rearrange and solve for volume just to make my algebra a little bit easier. So what I did was I divided both sides by pressure. Okay? So now I've isolated volume. So now I can solve for this. And now I'm going to plug in. So for N, 0.118 moles. For R, that's the constant. So I'm going to plug in the constant. I'm going to put in the units just so I make sure that I've canceled everything out. Temperature is already in Kelvin, which is great. 305 Kelvin. And then my pressure is 0.97 atmospheres. So if you do the math and you double check your units, right? Moles cancel, Kelvin cancels, ATMs cancels. We're left with liters, which is great because we solve for a volume. And let's see, I want two significant figures because 0.97 atmospheres is 2 sig figs. So I'm going to say 3.0 liters. So any gas under these conditions is going to take up a volume of 3 liters. Okay? And that is the ideal gas law in a nutshell, right? So when in doubt, if you have conditions where all 4 variables are at play, then you need to use the ideal gas law. If you have a scenario where only, 2 variables are at play, you can use one of the smaller, simpler gas laws in order to do that, okay? But this just gives you a sense of what the ideal gas law overall is, okay? So you're going to try to do a couple of these on your own. See if you can figure it out. Be careful of your units, okay? And yeah, we'll go from there, okay? And let me know if you have questions. All right, guys.